In this talk, I want to describe the necessary background to understand deformed G2 instantons and to give some simple examples. So to set the scene, it's going to be useful to think about one key example, the 7 sphere, and this will be useful for this whole series of talks. Now, the one thing that we know very well about the 7 sphere is that we have a Hopf vibration of the 7 sphere over the 4 sphere by 3 spheres. And using this vibration structure, we can describe the round metric on the 7 sphere as the sum of the round metric on the 3 sphere and the round metric on the 4 sphere. And I will call this metric GTS for reasons that will become clearer in later talks. Now, this metric actually appears as a special element in a one-parameter family, often known as the canonical variation. That's because this vibration has totally geodesic fibers, and it's a Riemannian submersion. And we see that the GTS round metric corresponds exactly to t equals 1 in this canonical variation for a parameter t, which is positive. And we can ask, is the round metric the only special element in this one-parameter family? What we mean by special is, when is this metric Einstein? That is, when is the Ricci curvature of this metric a multiple of the metric? And of course, by a multiple, I mean a constant multiple. And the answer is that there are exactly two possibilities. The first is that we take t equals 1 and we get the round metric that we already knew. The other possibility is that we take t is a special value, which happens to be 1 over root 5, and this metric we're going to call GNP, again for reasons that will become clear in a moment. So what we see is that we have two very special metrics on the 7 sphere, so two different Einstein metrics distinguished by this parameter t being 1 or 1 over root 5. Now, the other structure I want to explain on the 7 sphere relates to the group G2. So the way that we see that is that we can embed the 7 sphere as the unit sphere inside the octonions, the 8-dimensional norm division algebra. And then what we get is a cross-product structure on every tangent space to the 7 sphere, because every tangent space to the 7 sphere can be canonically identified with the imaginary octonions. And the cross product is just the skew symmetric part of the just octonionic product. Now, given this cross product and the round metric, we can build a 3-form on the 7 sphere, which is like a scalar triple product. We take two vectors, u and v, we take their cross product, and then take their inner product with w. So this looks a lot like the scalar triple product on R3, but now extended to 7 dimensions. And it turns out that this is a 3-form, so it's totally skew in the entries, just like the scalar triple product. Now, this 3-form is an example of what is known as a G2 structure. And that's because this 3-form, if we look at its what it is pointwise, the subgroup, the general linear group preserving that 3-form is isomorphic to G2. And so we can talk about G2 structures as pointwise looking like this model structure at every point. Or if you prefer, you can define the same model structure just on Euclidean space. So you replace the round metric by the Euclidean metric here, and you'll get yourself a G2 structure on R7 rather than S7. The important thing to know is that this G2 structure looks very special, but in fact, it's an open condition to be a 3-form defining a G2 structure, so it's just a non-degeneracy condition. Therefore, the precise formula is not important. What's important is that this 3 form is non-degenerate. So what that means is that this 3 form actually determines the metric. So that's what this non-degeneracy condition will give you. If you have a non-degenerate 3 form, it will determine a metric for you, and in fact an orientation as well. Now we can have a look at what special properties this 3 form has, because we know that this 3 form determines the metric, and the metric is special. It's the round metric. In particular, it's an Einstein metric. Well, we see that if we take the derivative, just the exterior derivative of this 3 form, it's a constant multiple of the dual of the 3 form. And this makes sense because if you have a 3 form in 7 dimensions, its dual is a 4 form, and so this equation is a valid one. So this formula is a very restrictive condition on your G2 structure 3 form. And this condition is called the nearly parallel condition. So now, this is what this NP refers to. It refers to nearly parallel. And as we'll see, there will be a 3 form defining this metric, which will also satisfy this same equation of being nearly parallel. And in fact, whenever you have this equation being satisfied by a G2 structure, then the metric that it generates will be an Einstein metric. Now there's one final thing I want to observe on this slide, is that if I take this equation and take the exterior derivative again, then I'll just get that this 3 form is co-closed. Or said another way, the dual of the 3 form is closed. So there's quite a lot of information on this slide, but it is very important that we keep this in mind as we go forward in this series of talks, because this is the model example that we have to want to have in our minds. Given all this, I can now tell you what a deformed G2 instanton is. So the setup will be that we have a 7-dimensional manifold X. We'll have a 3 form phi defining a G2 structure. So remember, that's just a non-degeneracy condition on the 3 form. And we're going to demand that it is a co-closed 3 form. So one thing that I should point out, of course, is that this star depends on phi, because the star depends on the metric and orientation determined by phi, and so this is a nonlinear condition. But it's an important condition, and it's one that we know is satisfied for our model 3 form that we had on the previous slide on the 7th sphere. And as I said in the introductory talk, we're talking about gauge theory. That means we need to talk about connections. So we're going to take a connection A on some bundle over X. Let's say it's a vector bundle, but it could also be a principal bundle. And then let us recall what it means for a connection A to be a G2 instanton. What it means is that if I look at the curvature of A, so that's going to be an endomorphism valued 2 form, Fa, then it satisfies this equation, namely that if I take the 2 form and wedge it with the star of the 3 form, so this is a 6 form, I want it to vanish. And you'll hear about G2 instantons in other talks in this series. Now, that's the regular G2 instanton. So what is a deformed G2 instanton? So this was a notion introduced by Li and Leung, and we will call these things DG2 instantons, just for short. And as the name suggests, you should take this equation and deform it a bit. And how do you deform it? You add in an extra higher order term, which is 1/6 the cube of the curvature. So What does this cube mean? It means that I cube the 3 form and I also take the third power of the endomorphism. And this makes sense because the cube of a 2 form is a 6 form, and so these two things can be equated to each other or combined in this way. So this is a perfectly good definition. You can write it down, but where does it come from? Where it comes from is this idea of mirror calibrated cycles. So let's just go back to a simple flat model, which is just 7-dimensional Euclidean space, which I can split up in this very simple way as R3 plus R4. This is a very important splitting in G2 geometry in general, that 7 equals 3 plus 4. Then I'm going to choose coordinates x and y on the R3 and R4 component respectively. And I'm going to recall that I can define my G2 structure 3 form as a scalar triple product using the Euclidean metric on R7 and the cross product, viewing R7 as the imaginary Ortonians. And what I discover is that I can relate this DG2 condition to the idea of mirror calibrated cycles in this setting in the following way. So let's suppose that I write down a DG2 instanton A, which is just a U1 connection. So that means it's just an imaginary valued 1 form. And it's not general in this case because you see the coefficients of the 1 form only depend on x. So suppose I have a DG2 instanton where the coefficients here only depend on x. And here I'm using summation notation. So the repeated j's get summed over, the repeated k's get summed over. Well, what is the condition for this A to be a DG2 instanton? Well, it's precisely the condition that if I look at the graph of U, well, what does that mean? That's a map from R3 into R4 because the U's, this got 4 components. And so this is a 3-dimensional submanifold of 7-dimensional Euclidean space. And so I can ask for it to be associative. And that means that the 3 form restricts to be the volume form on the submanifold. So this is a calibrated submanifold in G2 geometry. So that tells me what the U has to be. What does the little a have to define? The little a has to define a flat connection on this associative submanifold. So we can see that DG2 instantons of this special type are exactly the mirrors to a pair of an associative submanifold and a flat connection, or at least an associative graph with a flat connection. And this gives a good motivation for the definition of DG2 instanton, because one might hope to study such things and potentially count them. Now that's what happens if you assume the coefficients only depend on x. What if, instead, they only depend on y? So the same thing, but now I only let the coefficients depend on y. Well, then I can now have a look at the graph of V. This is a map because V has 3 components, V1, V2, V3. This is a map from R4 to R3, and so its graph is a 4-dimensional submanifold of 7-dimensional Euclidean space. I can ask for it to be co-associative. So that's the condition that the 4 form, star phi, restricts to be the volume form on the submanifold. So again, it's a calibrated submanifold. But what about the B's? Now they have 4 components, these B's. They depend on y. Well, it turns out that they have to define an anti-self dual connection, or ASD for short. And let's remind ourselves what that means. That means that the curvature 2 form, FB, is minus the Hodge dual of FB. And this makes sense because we're in 4 dimensions. On a 4-dimensional manifold, we can take the dual of the curvature, and that will be a 2-form again. So this makes sense. And so again, one might hope to relate these pairs of a coassociative and an ASD connection to enumerative invariance. And so they form a natural object to study in G2 geometry, and therefore compels us to study DG2 instantons. But we've seen in both cases that we've been talking about U1 connections. So here and here, they're U1 connections. And so our primary interest, and in fact what we will talk about for the rest of this sequence of talks, is just U1 connections. So now I'm going to talk about some examples of GG2 instantons that we can get very quickly from lower dimensions. But to explain that, I want to remind you how to do this in the case of G2 instantons. So recall, as I defined on the previous slide, that a G2 instanton A is a connection whose curvature 2-form wedges with the 4-form to give 0. Now, let us see how we can relate this to some well-known geometry in 4 dimensions. So let's always just take the flat model for simplicity. So we'll split up R7 into R3 plus R4 and take the natural projection map from R7 to R4. If we choose coordinates, X on R3 and Y on R4 as before, then we can define some nice 2-forms on R4, which are our standard hypercalar 2-forms defined here. So omega 1 is dy0 wedge dy1 plus dy2 wedge dy3, and so on. So we have a cyclic permutation of 1, 2, 3. And then we can write down this 4-form star phi explicitly as follows. So it's not too important what the formula is, but what we can see is that from this formula, we can immediately deduce the following result. It says if you have a connection B on R4 and you pull it back to become a connection on R7 and ask for that connection to be a G2 instanton, then what does it mean? Well, its curvature 2-form will always wedge with this to be 0, so that's no condition, but it has to wedge with this one to be 0, this one to be 0, and this one to be 0. But omega 1, omega 2, and omega 3, they span the self-dual 2-forms on R4, and so the G2 instanton condition on the pullback of B is exactly saying that B is an AD instanton on R4, i.e. the curvature is anti-self-dual. So you could think of G2 instantons as the 7-dimensional version of anti-self-dual connections in 4 dimensions. So that's one way to relate things to lower dimensions. You can also do the same sort of trick with 6 dimensions. So now you split up R7 into R plus C3. You have a projection map from R7 to C3. You choose a coordinate T on the real line. You have a calar form, omega, on C3, and a holomorphic volume form, capital omega, on C3. So these are the standard structures when you think of C3 as a Calabi-Yau threefold. Then you can ask, suppose I have a connection on C3, if I pull it back, when is it going to be a G2 instanton? And so for that, we need a formula for the 4-form again, and here it is. And now we can check exactly the condition that I said. When is the pullback of a connection on C3 a G2 instanton? Well, then it's going to have to wedge with omega squared to be 0, and it's going to have to wedge with the imaginary part of omega to be 0, because this dt makes those two things independent from each other. And what does that mean? That is exactly saying that the connection is Hermitian Yang-Mills. Namely, that the 0,2 part of the curvature. So that's using the PQ decomposition of forms on complex manifolds. We're asking for that to be 0, and the other condition that I said, that you wedging with little omega squared to be 0. So this first condition comes exactly from wedging with im omega to be 0. And Hermitian-Yang-Mills equations, of course, have been very well studied, and it's known that existence of Hermitian-Yang-Mills connections is equivalent to the bundle being stable. So this is the Donaldson-Uhlenbeck-Yau theorem. And so one might hope that, at least for these special G2 instantons, one can understand their existence in terms of a stability condition, though that seems too much to hope for in general. So this is something that we already know very well, hopefully, at least now. So what do we do in the deformed G2 instanton case? How do we relate things to the lower dimensions? Well, let's have a look at the 4-dimensional version. So we have a projection map from a 7-dimensional manifold to a 4-dimensional anti-self-dual Einstein 4-manifold. So this is basically the same as the situation we had before. It's just I've made this a more global statement. Everything I said on the previous slide would have applied to this setting, but it was simpler to say in the case when X was just Euclidean space and Z was a 4-dimensional Euclidean space. And then, if you have a connection B on Z, you can ask, when is its pullback a DG2 instanton on X7? Well, it's exactly the statement that B is anti-self-dual again. So in fact, nothing changes from the G2 instanton case. So that's slightly less interesting than we might hope, but it has the nice feature that we already get from AST instantons on S4, which are very well understood. We get DG2 instantons on the 7 sphere, because that's exactly one of these situations, in fact, just given by the Hopf vibration that I mentioned right at the beginning of this talk. But ultimately, 4 dimensions wasn't that revealing, so let's go to 6 dimensions. So now we have a projection map from a 7-dimensional manifold to a Calabi-Yau threefold, which has real 6 dimensions. And remember that we need to, that what this means is that we have a Kähler manifold whose holonomy is contained in SU3, holonomy of the metric is contained in SU3, and it has a Kähler form, which we'll denote by little omega still, and we're going to take a connection B on this Calabi-Yau threefold Y. And we're going to ask the same question, if I pull back that connection B, when is it a DG2 instanton? So, given this lemma, you might guess that it has to be Hermitian-Yang-Mills again. But actually, what happens is something slightly different. It turns out that B has to be what's called deformed Hermitian-Yang-Mills. And this motivates the name deformed G2 instanton. And what does it mean? It means that the 0,2 part of the curvature is 0, so that's exactly the same as the Hermitian-Yang-Mills condition, but the second equation is deformed. Now we ask for the imaginary part of omega plus FB cubed to be 0. So you see that we get from this, we get the FB wedge omega squared term, because remember that F is imaginary valued, so you'll get that F wedge omega squared term, but you'll get another term from the cube of F. Now, as I mentioned on the previous slide, there's a relation between Hermitian-Yang-Mills connections and stability. And there is a conjecture that the same thing should be true for deformed Hermitian-Yang-Mills, which I've abbreviated to DHYM, that their existence should correspond to a stability condition. And there's been exciting progress on this in work by Collins, Jacob, and Yau, and also by Gao Chen. that concludes this talk on the background of DG2 instantons, and next time we're going to talk about the results.